Hello. In this demonstration, I will show how to use model weights to address imbalanced data. I'll apply the weights to classification, but you should know that PySpark supports other weighted models. So here's some data. As you can see, there's a bunch of transactional data, 99% of which are no fraud, no problems at all. But 1% is fraud. And we're going to train our model on this data set. The problem is that most algorithms assume there's a normal distribution. So the algorithm won't perform so well if this is the data we're given. So the idea is we're going to modify the data or modify the algorithm in some way so that it produces a better model. So there's a couple ways. One is to resample the data. So on the right here, I've got a bunch of data and I've got lots of blue. So I'm going to reduce or undersample so that I get an even amount of blue and orange data. The other way is oversampling, where I've got a little bit of orange data and I'm going to resample to produce this greater and equal amount of orange data as an example for classification, where I'm classifying orange or blue. So this is very common, but it's not so good for big data, because if I've already got a big data set and then I take my orange and I basically doubled my data size, then I've got a problem. So another thing you can do is use different metrics in order to determine a good model. And F1 score or the area under the curve for a ROC curve are good. But I would say it's more common for big data to use class weights. A lot of the modeling algorithms have weights so that you can adjust the algorithm to appropriate model given data that's unbalanced. So we're going to make these algorithmic adjustments in proportion to the data. So the weights will be inversely proportional to the class frequencies, which I'll show you in a moment. So in particular, we're going to use these weights, and that's what I'm going to demonstrate, for big data sets, because it's going to work better than making a bigger data set. So here's an example. I've got 9 rows of data. That's my sample size in this formula. And I'm going to calculate the weight for a particular class C. And the way to do it is, by this example. I've got 9 rows. I've got 3 different classes. So I've got 3 different classes. And in particular, I've got 3 cats in this data set. So 9 divided by 3 times 3 is 1. That's the weight for the cats. For the dog, it's 9 divided by 3 times 5, because there's 5 dogs, and that's 0.6 is my weight. In horses, the weight becomes 3. So this is how I'm going to produce weights for my data set. So conceptually, that's how it's done. How do we do it in PySpark? I've got a regression model here, logistic regression for binary classification in this case. I've got a class, but there's no weight. This is sort of the standard way of doing it. But next, I can use this weighted column, which is common to a number of the PySpark algorithms, and I'll use a weight. And somehow I've got to calculate those weights so I can do the formula I showed in the previous slide. And for class 1, the weight is going to be 289. And for class 0, no fraud, it's going to be 0.5. And you can see the counts of each of these, how many rows of data I have that have class 1 and class 0. So when I go and look at my actual data, it's going to look like this. It'll have the class, and I'll have this new column that's a weight, and that weight, that column there, that's the one in my data set that the algorithm is going to refer to. So when it looks up the labeled column, it's going to associate that weight with that class. So what's the result of this? Well, if I have unweighted and I'm doing the example I'm going to show, the area under the curve for ROC is 0.97, but weighted is 0.98. So it's a little bit better. It also can show up when you do confusion matrix, which you can see probably best here on the right. If the actual value is 0 and we predicted 1 being fraud, we got about 36% of the time. But on the other hand, if we use the weighted, then when it was actually 0, we predicted fraud about 8% of the time. So by doing weighted, we made quite a bit of difference in how our model predicted things. It predicted fewer false positives. And same thing here, if I have a multi-class classification, which I have here, there is 6 classes. All of the classes in this diagonal are predicted better. The only one that's worse is the first one, where the actual class was 0 and we predicted 71% of the time here on the left unweighted, where it's 42.9 on the right. So generally, and the idea, of course, is that the weighted model will perform better than the unweighted model. So let's go to a Databricks demo and see if it works. So here I am in a Databricks notebook, and I've got some data I've downloaded for credit card data. And I'm going to read that data into a Spark data frame. All right, we can look at the data, display the data, and I just want to point out this data is going to be unbalanced or imbalanced. On the left, here's sort of a common case where the data looks pretty balanced, not a big deal, but on the right, there's quite a bit of difference between the classification of fraud versus normal transactions. So, as I mentioned in the slides, there's different ways to do this, but the way that we're going to improve our models with class weights for the model. And what we can do is count up our different classes, and we see that the fraud is 492 in our data set, and the non-fraud regular transactions is about 284,000. So I've got some functions here to compute the class weights, which I'm going to use in my algorithm. So the first thing here is I got a function for class weights. It's given a column, I'll compute the weights. And it simply does a count of the different classes. Then I total up the number of classes I have, the sample size, and then it does the calculation we saw before, the total sample divided by the number of classes times the count for that particular class. So that gives me my class weights. And I need to add this to my data frame so that I can do the processing. So I need a new column, a weighted column that's associated with each class value. That's what this this function here does. And you can see that it's applied like this. I'm going to apply this weighted column function to a Spark data frame in a particular column. So in this case, it's my class column. It has all the classifications, the different classes. And I'm going to pass in some weights. So first I'm going to calculate the weights, and that's what I've done above here. That's what this function does. It calculates the weights. And then those weights are going to be passed in to my function called weight column. And it's really a user-defined function. Here it is here. Weight is a weight column UDF is a user-defined function. And as you can see, it's a pandas UDF, and it applies to a column and returns a column. And so it's going to apply to this this class column. Okay, but I need to pass in the list, and so there's a common way to pass in a parameter to a UDF user-defined function, and that is define it within the scope here. So here's my weighted column. I pass in my weights, and then the UDF relies on that lexically defined parameter weights. Okay, so let's go ahead and look and see how it works, and hopefully that'll make sense. So here's my class that has, my data frame that has all my data is called DF, or data frame, and I'm going to go ahead and compute the class weights for it, and then you can see here, this is where I get my one class is 289 weight, and then the 0 class is 0.05. I go back up, you can see that this is my, my data frame that I read in. So DF is my data frame I read in. Okay, so now I want to add a column to my data that has those weights. So I'm going to take my data frame, I'm going to make a new column with column. It's going to be called weight. I'm going to apply the function I wrote above. It's a user-defined function for a data frame, and it takes in the class it's going to apply to, the column that it's going to apply to. In this case, it's the class column, and it takes in a dictionary of class weights, and that is defined by the class weight function. So anyway, the result of this is I get my new column called weight, and if I do a group by and so forth, I can see that the columns for the weight for classes with value 1 is 289, and the weight for classes with 0 is labeled 0 is 0.5. And again, you can see that the counts are the same. So to make it a little bit more clear, I hope, here's my overall data frame. It's called credit card fraud. And if I scroll to the right, there's all these different values from the data set that help you predict fraud. But if I scroll to the right, I should get my new column here called weight. And you can see that for all the values of class 0, it has the weight of 0.5. And they're pretty much all 0.5. But if I could scroll far enough down, I would eventually come to a 1 in the value for 1. The weight would be 289. All right, so now I've got my data frame that has my original data, but then it also has a new column for weights associated with those classes. Now I'm ready to go ahead and run my modeling, my logistic regression. So this is the standard way of doing logistic regression in PySpark. I've got a pipeline. In this case, I've got an R formula, which is going to predict the class using the other columns. And in this case, I don't have a weight. So this is a standard case, just the standard way of doing a model. And I take this pipeline, which is my R formula followed by logistic regression, and I apply it to the training data in order to get a fitted model. And I can pull out the logistic model from that pipeline. It's called LM, and I could do a summary. And I've just written a function here to print out a summary of what that logistic model looks like. Here's a formula, here's the equation, here's a summary of the area under the curve, the rock, and accuracy and false positive rate, true positive rate, and so forth. So let's make a note of this so we can compare it. So the area under the curve rock is 0.97. We can also look at the confusion matrix and see that, as I showed in the slide introduction, the actual value is 0, and sometimes we predicted fraud incorrectly 36% of the time. Okay, and this is just plotting the rock, and again it's 0.97. Now let's go ahead and do the whole thing over again, but the difference is I've got logistic regression with my weighted column. So remember, I prepared that column that added the weight, and so if you remember back the data, got the regular old data, rows and rows of data, as a class, labeled class indicating what class it is, 0 for no fraud and 1 for fraud. And then I added in the weight using the calculation that we use for based on the frequency of that class occurring. All right, so now we're going to go ahead and add that weighted column, and everything else runs the same. I'm going to fit my model using the weighted logistic regression. I'll pull out the logistic model, and that'll do a summary. Same summary as I did before. And this time, the area under the curve of the rock is 0.97 instead of, 0.98 instead of 0.97. And the other values are slightly different. But perhaps most notably, when we look at the confusion matrix, the actual fraud was 0, but we predicted 1 incorrectly 8% of the time here. So 8 is much better than before, which was 36 and almost 36.5. So adding the weighted column helped us here. Okay, so that's how you do it for, and we can plot the rock too. That's how you do it for binary classification. Now just to continue with multi-class classification, it all pretty much works the same. So I'm going to read in some data. I can look at the data. I'll put all the faults, basically all the different classes in one column. I've got my fault column here to the right. Okay, and I can go ahead and compute my class weights based on that fault column using the same function I did before. And you can see now I've got different weights. It's not just 2 classes. I've got, I think, 6, 7 classes. Now here are the weights for those classes. You can see the class and then the count, and then the associated weight. So we did this with our weight column user-defined function, or weight column UDF, which takes in the class weights as a dictionary and then creates this new column called weight. So that's what we got. So once we have that weighted column, and you can see it here, far right, same as our other example. You can see they have different weights for different classes. Now let's go ahead and run the pipeline for this. And once again, I'm just using the same old logistic regression. This is multi-class logistic regression. There's no weights. I'm going to fit the model to the data. I can print out my summary. Now, I'm not going to get a rock for this because this is not binary classification, this multi-class classification. You can look at accuracy here to see how it is. But again, the confusion matrix is probably a better example, better measure of how things are going. I've got 71 here, and we can see all the others as well, or how well we're predicting the actual values. Okay, so now let's go ahead and do the same thing again, but using that weighted column that I've constructed, using the frequency of the classes. And I can look at the summary again of the values. The accuracy is what? 0.79. Here in the previous accuracy is 0.75. So even accuracy has improved. Okay, and then I can also go ahead and do the confusion matrix. And while the first value is a little bit less, 42, I believe all the others are improved. So that's how we do weighted. That's how we add weights to a model in order to address an imbalance of the data. So I hope that works for you.